discussing about the Zaghi bearing capacity theory. And just now one of you was able to recall the equation, and that's how it looks like. Okay, so we were able to divide the soil around the foundation into three main zones, according to the Zaghi's theory. And you see this wedge immediately below the bottom of the foundation. We saw that Zaghi assumed the angle of this wedge to be equal to the friction angle of the soil. But later on, through experimental studies and field practice, they actually found out this angle, alpha, is closer to 45 plus 5 or 2. So because of that, they made some modifications to the initial bearing capacity from the Zaghi. And this is how the equation looks like. So they added shape factor, depth factor, and load inclination factors, right? And also the bearing capacity factors that we used last time, now for this case will be different because of the difference in the angle, okay? So today we are just going to go through some examples using this modified bearing capacity equation. And yeah, I think that will give us a better understanding of how to use the equation. And if you have any question, please feel free to stop me and ask me. Okay. So let's start with this example. Okay. So we are told that we have a square column foundation that is 2 meters by 2 meters in plan. Okay, and the design conditions are depth of embedment is 1.5, as can be seen in the diagram, and the unit weight, gamma, is 15.9, right? The friction angle is 34 degrees, and the cohesion is 0. So this probably is some kind of sandy soil, cohesionless soil generally. So we are asked to obtain the allowable gross vertical load that the column could carry. And they give us the factor of safety to be 3. All right, so we are supposed to use Meyerhoff's equation. Meyerhoff's equation is the modified bearing capacity equation that we just seen. All right, so we have this formula for the allowable bearing capacity. Well, if you want to get the allowable bearing capacity, you have to divide the ultimate bearing capacity by the factor of safety. So that's the only difference with the initial equation. So the first term becomes 0 because this soil is cohesionless. So we do away with the first term and you are left with these 2 last terms, okay? Right, so the next step is the first step is to get the bearing capacity factors. As I mentioned to you, because this is a modified form, the bearing capacity factors will be different. And I've been able to display the bearing capacity factors that we're going to use for this problem. And the main factors that we are concerned with is NQ and N gamma. Remember, NC belongs to that first term of the equation, which we cancelled, so there's no need to look for NC in our case. So because the friction angle is 34, we have NQ as 29.44 and N gamma as 41.06. All right. The second step is to calculate the other factors that are in this equation. So these factors mainly divided into 3. Shape factors, that is to do with the shape of the foundation, right? Remember, the Zaghi bearing equation would only deal with square footing, strip footing, but probably do not deal with rectangular footing. So with this equation, you can deal with different kinds of shapes, and there's a factor to take that into account. So we have two shape factors, right? So this is the equations for the shape factors. So here is just putting in the values. For example, B is the width of the foundation, L is the length. The foundation is square, so both dimensions will be the same, 2/2. The friction angle is 34. So we have that as 1.675, right? This other shape factor, which belongs to the last term of the bearing capacity equation, takes this form. The same thing, B over L is 2/2 because this is a square foundation. Okay, so this is 0.6, right? The next thing is the depth factor. And for the depth factor, one thing that you should consider is the ratio between the depth of embedment of the footing, right? That's the distance from the surface, the ground surface to the bottom of the footing, okay? So that ratio, that's divided by the width of the footing, will determine which depth factors we use. So for our case, the depth of embedment is around 1.5, and the width of the foundation is 2. So that I think that falls within this criteria. The depth of embedment is less than the width. So from that, we use these equations, okay? So we have the friction angle. I think this is just a matter of inputting the values and getting the factors, right? Gamma D is taken to be 1 under these conditions, right? And the final factor is the load inclination factor. So if I remind you, so far we've only dealt with loads that are vertical, but in practice you might find different situations where the load is inclined. So you won't always find a case where the load is vertical. It might be inclined at some angle, and this load inclination factor tries to take that into account. So from our example, the Q is vertical, so there's no inclination. This inclination, inclination angle theta, is going to be 0. So for this inclination factors, all going to be made to be 1. Okay? And so finally, the last step is to calculate the allowable bearing load. So remember, this is the equation that we have, and we have to divide this ultimate bearing equation by the factor of safety to get the allowable bearing capacity. So after we input all these values that we calculated through those steps, we end up getting this as a allowable bearing capacity. But I should remind you that the question asked for load. So load and stress are use two different units. So here we have the stress, or maybe you can say capacity, right? So it's per meter squared. If you want to get the load, you have to multiply it by the area. Then you can be able to get the final load, as you can see there. So, any questions so far? No more questions. All right. So I have an example for you to do. Just the same question and same parameters. The only difference is now the load is inclined at angle beta. And to make your work easier, I calculated the factors for you. But probably in your homework and also maybe in the exam, I'm not sure, you might have to get these factors on your own. So this is just like to facilitate like the process, make it a bit easier for you. So I think I give you some units to calculate the vertical load, then probably we can continue from there. Yeah, so just a reminder, this is the equation for the bearing capacity. Once you input all these values, you divide by the factor of safety, you get that, then you have to multiply it by the area. This is a square footing, so it's the area is 2 by 2, it's going to be 4 meters square. Okay, so so just a reminder, this is the surcharge here, Q, right? You calculate it from the ground surface to the depth of the footing. So that's going to be gamma df. Gamma is 15.9. So anyone finishes, just raise your hand.
sí comenté que era tóxico.
Because that's already stress. So you multiply to get the load. Yeah, so I think this should be the answer that you get once you do your calculations. It should come to around the load should come to around 1457 kilonewtons, right? And one interesting thing that you should note, you see this load 1457. If you check the other question where you had the vertical load, the capacity was bigger, right? The soil capacity was bigger, I think around 2400. So it seems like if you load it back the soil vertically, it's able to take more load than if you load it at an angle. But that's just something, a side note, not very important. Okay. Yeah. So any questions? Any questions on that problem? Okay. All right. So let me move on to another problem, a bit more challenging, but not so much. So last week, Professor Lee went through some scenarios where you have groundwater. Okay. You have different cases for groundwater. You can have the first case, as you see there, where the groundwater is above the bottom of the foundation. Okay, at a level D1. Let's say D1 is the distance from the surface to the water table. Okay, so when you calculate the factor Q. The Q is the surcharge that you used in the previous equation. All right, you will calculate. You will have to factor in the difference in unit weight. Okay, above the foundation, above the water table. Sorry, the unit weight is the normal unit weight, moist unit weight, right? Gamma. But when you go below the foundation, below the water table, you have to factor in the unit weight of the water. And because what we are looking for is the effective stress, you take the saturated unit weight and you minus the unit weight of the water, okay? Because we want to get the effective unit weight, because we are dealing with effective stress. Okay, so that's the only difference. If you encounter this case, that's how you go about it. All right. The second case is where you get the water table at a certain distance below the bottom of the foundation. Let's call this distance D. Okay. Now for this distance, if you are calculating the surcharge, it will be the normal gamma dF. Surcharge, remember, is the weight of the soil above the bottom of the foundation. Okay, so that will be gamma dF. But the last term of the bearing capacity will have to be modified, because you have to factor in the unit weight along this distance, which is just going to be gamma, the normal gamma, but also the effective unit weight once you go below the water table. Right? So this situation you encounter it most of the time in practice, but for the sake of simplicity, we will not. I will not go into examples showing this. The third case is where you have the water table at a very large distance from the bottom of the foundation. So in such a case, if the distance from the bottom of the foundation to the water table is greater than the width of the foundation, then the water table will have no effect on the ultimate bearing capacity. So in such a case, you can neglect the effect of the water table. The surcharge will be the normal gamma dF as we've used in the previous case. Okay, so these are the three scenarios that Professor Lee highlighted in last week's class. So based on that, we are going to go through two examples. Let's start with this one. Okay. So we have a column foundation that is 3 by 2 meters in plan. All right, and the depth of embedment is 2 meters, as you see here. The strength parameters, phi is equals to phi friction angle, and the C prime is 50. Okay, so the factor of safety should be 4. So what they're asking us is to determine the gross allowable load the foundation can carry. All right. So first of all is to gather the information you have. We have the soil parameters, like because we have soil that is above the water table and below the water table, the unit weight will be different. Above the water table, that is the normal gamma. Moist unit weight is 16.8. Okay. Below the groundwater, we have the saturated unit weight of the soil, so it's going to be slightly larger. Okay, it's going to be 19.4. All right. This is the width of the foundation, 2. So B is equals to 2. L is going to be equal to 3. All right. So let's go to the next. Let's go to the first step. The first step for this case, where you have the groundwater, is to identify which type of groundwater case you're dealing with. right? So if we have the water table above the foundation, I think we are dealing with the first case, right? And we have to calculate the surcharge, right? Because the surcharge in this case will be different due to the effect of the groundwater. So using the formula that I showed you, we start with gamma df, okay? Gamma df plus so what we are looking for is, no, sorry, this should not be gamma df, this is gamma d, gamma t, no, it's gamma df. But what we are looking for is to factor in the effect of the groundwater. So we are going to calculate this using this formula. So this is going to be 16.8 times 2, then plus 1. Where do we get this 1? This 1 is the distance from the groundwater to the bottom of the foundation, right? Now this one, we say that below the groundwater we use the effective unit weight. So we are going to calculate that by having the saturated unit weight 19.4 minus the unit weight of the water 9.81. All right. Then we get this value 26.39. That is the effective surcharge that you use for this kind of problem. Okay. I hope you can follow. I know probably it's not as simple. So if you have any question, please ask them. And bearing capacity factors is our second step. As I said, once you know the friction angle is 25, you just read it from the table. You can have either these tables or you can have equations for which you can calculate these factors. So here we need all these factors because we have a cohesive type of soil. Cohesion is equals to 50. Right? So those are the factors that we use for this problem. The other step is to look for the shape, depth, and inclination factors. Okay, so these factors, we start with the shape factors, and as I highlighted earlier, it's just a case of knowing the formula and just replacing the values. So B over L, we know that B is equals to 2, L is equals to 3 from our problem. NQ, NC, 10.66, 20.72. So we get this value. The same thing with the next shape factor. The B over L, 2 over 3, tan of friction angle, 25, we get this. And the last one, we get this kind of value. All right? So this is just the same as the first example that we did. The only difference is the calculating the surcharge. That's the only difference because of the water table. But the steps after that, all the same. Okay? So to move on to the other factor, depth factor, as I highlighted, this factor, you have to get the ratio of the depth of embedment to the width of the foundation. So for this case, depth of embedment is around 2. The width of the foundation is also 2. So it's more or less equal to the depth of embedment is equal to the width of the foundation. So equal to each other. So we use these formulas, all right? And these are the factors that we get. Okay. And the load inclination factors. So for this case, is our load inclined or is it vertical? What do you think? This load, is it vertical or is it inclined? Vertical, right? Yeah. So beta is going to be 0. So all these factors are going to be equal to 1. Okay. So that makes life easy for us. All right. So the last step now is just, since you've collected all this information, you just put it in the equation. Okay? Our equation is going to be a bit longer because now we have the cohesion component. And we have to factor in all these calculations. All right. So after doing all these calculations, we get the allowable bearing capacity. And because they ask for load, as I mentioned earlier, you have to multiply this capacity by the area. The area is going to be 2 by 3. Okay, so you get this load, 3760 kilonewtons. So that's your allowable bearing load. That is what the soil can take, like from your building or from whatever structure that you're dealing with. All right. So any questions? Yes?
Why the gamma prime isn't in the equation, and we solve first for the gamma prime, but in the equation we don't have?
Here?
Yes.
Oh, okay. So gamma prime, like in the equation that you are dealing with, we have two factors that are going to change due to the water table. First one is Q, the surcharge. That is what we are calculating at the first stage, right? So I say that you have to factor in, let me go back. So you have this, you have to calculate the effective surcharge. You have gamma df and you have gamma d2 and times gamma prime, right? So it is not in the equation, but if you put the q, you know very well what you're supposed to do or how you're supposed to calculate it. Another equation of interest that also touches on that is this gamma. Because this gamma, normally for the bearing capacity equation, is the unit weight of the soil below the foundation. Okay? So if we look at this figure, below the foundation, what is the unit weight of this soil? It's below the groundwater, right? So if it is below the groundwater, we have to get the effective unit weight, gamma prime. Okay, so that's going to be 19.4, the saturated unit weight minus the unit weight of the water, 9.81. Right. So if you look at this equation here, you see it's 19.4 minus 9.81. Okay, then times the other parameters, the width and so forth and so forth. You understood?
Yeah. Thank you.
Okay. Any other question? Yeah. Okay. So I just go through another example. Just go through this one quickly because we don't have a lot of time. So it's the same example, just different parameters. Depth of embedment is 1. The friction angle is 32. The cohesion is 0, some type of cohesion-less soil. The factor of safety that they've given us is 3. And they asked us to determine the gross allowable load the foundation can carry. So we should use this bearing capacity, shape, and depth factors. Okay, so the first step, we identify the groundwater case. Which case is it? It's the first case that Professor Lee explained last week. So we have this formula to get the effective surcharge, gamma df, okay, times plus df minus d1, which is the distance from the water table to the bottom of the foundation. Now times the unit weight. Okay. From there we can get the effective surcharge. All right. The second step is to get the bearing capacity factors. This one is an easy step because you have the friction angle. And since our soil is cohesionless, the first term of the bearing capacity equation is cancelled. It has no use. So if you're looking for bearing capacity equation factors here, you don't need to look for NC. So we have NQ and N gamma. All right? The same procedure as the other questions that we've looked at. The third step is to calculate the depth, shape, depth, and load inclination factors. And the same procedure as before. Just to remind you, this is a square footing. So B width and the length is the same, 1.2, 1.2. So if you come to calculate these factors, just put 1.2, 1.2, and you get your values, right? The depth factors is calculated as shown. Depth of embedment is around 1. The width is 1.2. So it satisfies this criteria, and we use these equations. If the depth of embedment is greater than the width, then they will give you different formulas to deal with that. Okay. Lastly, we have the load inclination factors. So luckily, our load is vertical, and that means less work for us. Okay, so it makes life easier. And we have these factors as 1. Okay. So what we do, the last step, we calculate the allowable bearing load. Then we have the factor of safety as 3. We have calculated all these other factors, all right? So we just put them here. So one thing to note, as she asked, the difference with the water table cases is going to be mainly from this Q, the surcharge, and also this gamma. Please note that this gamma that we use, the last term of the bearing capacity equation, is for the unit weight of the soil below the bottom of the foundation. So that's something that you should remember when you are doing your calculations. Right? So you input the values and you can get the allowable bearing capacity, and eventually, because they are asking for load, you should multiply by the area of the foundation. So in this case, it's going to be 1.2 by 1.2. Eventually, you get your allowable bearing load as 336 kilonewtons. Okay. So this, I think, are typical questions for foundations that you can encounter. I've tried not to go into very difficult or complicated examples, but I think with these practical exercises, you can be able to learn how to use the modified bearing capacity equations, right? Yeah, so I think that's all. If you have any other questions, feel free. Yeah.
Can I see the Q calculation, please?
Q.
Yes, Q.
This, okay.
Yes, DF is 1, right? DF.
Yeah.
DF is 1 or 0.5?
No, sorry, this DF should be D1, if I'm not wrong. I think when I was copying this equation, I made a mistake. So please note that when you are calculating this surcharge, first of all, we calculate this part. So this case is going to be 0.5, okay? Then after that, we calculate the remaining part, right? Sorry for that, sorry. But when you're calculating the surcharge, because you have to calculate the unit weight of the soil above the water table and then below the water table. So this is not gamma D, this is gamma D1, right? So it's going to be 0.5, and then below the groundwater another 0.5, as you see here. Okay. Because the unit weights are different. And that's a point of correction. Yeah.